Okay, team, here we go. Oh my God. Okay, see if we can do this without an echo. Seems to be good. Okay. In order to avoid the same problem I had last week, I'm dialed in on both my phone and my computer so that it sees two people, so it doesn't decide to end the move or end the meeting because there's no attendance. Give me 1 second. I'm going to start this slideshow. Have it. Can you all see that okay? Okay. Take 2 minutes, get yourselves a coffee. I'm just going to set up here and make sure that the door is closed so I don't wake the family up. And I will be right back. Excellent. Okay, we're going to take another crack at the structure of enclosure. Great. Okay, so we've talked extensively about all of the various control functions or the various functions of your enclosure. And you'll recall that the major ones that we've covered are management of heat, management of water, management of vapor, management of air. Those are the kind of four major environmental ones. And then we talked about some secondary ones. Your enclosure has to manage access, so egress, letting people in and out. It's got to manage insects. It's got to manage sound. It's got to manage fire. And all of this it can't do unless it provides structure. That's not to say that it has to be load bearing in the sense that it has to carry the weight of the roof or the floors above. It doesn't. But all structure is subject to some amount of loads. It's got its own self weight. It's got wind applied to it. It's got interior pressures. Even interior walls have wind load on them. So that's what we're going to talk about today. So the first one we'll talk about is masonry walls. Or the first type of wall we're going to talk about is masonry walls. Probably because we spent a lot of time talking about masonry walls. You'll remember the kind of perfect wall was a masonry veneer, or the institutional wall, sorry. Masonry veneer, drained cavity, insulation, membrane, concrete block, and finish. And that's what's represented on the left side of the screen here. I'm hoping you can see my my cursor here, so that I can point to things. So within the masonry wall, the outer layer is the brick veneer, and that's the first layer that receives the wind load. When the wind blows on the building, it hits the brick veneer first. That load gets transferred back to the backup wall through brick ties. So the masonry veneer is connected to the backup wall at a close spacing of somewhere in the 400 to 600 millimeter grid. You can see the masonry veneer at the bottom is supported on a shelf angle that is suspended off the structure. It'll be connected back to a beam or something. And look at this, we've got a little gap at the top of that masonry veneer. That has two functions. One is it allows some degree of pressure equalization. The masonry veneer, the brick veneer, will have weep holes at the bottom to drain the cavity, and it has a gap at the top, which allows air in and out. What we want to do, to the extent possible, is equalize the pressure on either side of that wall to keep differential pressure from driving rain through the wall. So we've got the brick veneer, which spans the brick ties, which transfer load back to our exterior wall concrete block backup. For concrete block, what you need to do as architects is you need to understand proportion. So your engineer is often going to do the calculations, but you have to design proportion because it informs the informs all of your assemblies. So you have to get proportion right, but also your structural engineer is designing the structure for the building, is not doing your calculations for your various assemblies. That's on you. Calculations, by and large, are not hard, but they are the architect's responsibility for the non-load bearing assemblies. Okay, so how do we size concrete block? Well, it's really very simple. We use this depth to span ratio, and you'll see ratios like this all over the place. The thickness of this wall has to be more than the height divided by 20. It's that simple. For a 3.6 meter wall, height divided by 20 is 180 millimeters. 180 millimeters, you round up to the next block size, gives us 190. So that's the simple first rule. The second rule is the backup on an exterior wall can't be thinner than 190 millimeters, which is nominally an 8-inch block. So 190 millimeters, H/20, that's how you size your exterior wall. Now, what happens if there's windows, punched openings? Well, the masonry standard gives us a way of dealing with that too. The H/20 rule applies to a wall that is 85% solid, measured between any 2 points. Sorry, not any 2 points, between the center of two solid panels, 85% solid. If it's less solid than that, so over the same width, you have less wall doing the work, you need to be stockier. The proportion changes down to the point whereas if you're only 20% solid, then your rule changes to H/10. And then there's a graduated scale in between. So what does 20% solid look like? Well, let's say that you have a 4 meter wide window every 5 meters. So if you cut a plan section, you have a meter of solid, 5 meters of window, a meter of solid, 5 meters of window. That would be considered 20% solid. 1 meter out of 5 is solid. That's true even if it's a skinny little strip window. You can have a window that looks 99% solid, but you've cut a little strip window in it. You cut the section through that window, and at that section, you have 1 meter solid, 5 meter window, 1 meter solid. It's 20% solid for the purpose of application of this, because you've cut that little strip. Okay. So H/20, 190 millimeters, 85% solid, or else you change your H/20 rule. And that's really what it takes to select your backup block. You can do an engineered analysis like everything else. You can do more detailed calculations. You can get slightly generally less conservative results. But this H/20 has lasted for a long time. Look at the detail at the top of this wall. The masonry doesn't go right to the tight to the underside of the slab. You got two little clip angles at the top, and an airspace. What this is doing is it allows the upper slab to move relative to the lower slab, without that exterior wall becoming an unintended load path. Now, you might say it's an 8-inch concrete block and can take lots of load. That is absolutely true when you're dealing at a house scale. But if you've got a 10-story building or 20 or 50-story building, and this is your wall assembly on the perimeter, that concrete block wall can't carry all that load. And we don't want it accidentally trying to carry that load by virtue of the fact that we've put it in tight. So we make sure that we allow gaps that prevent unintended load paths. To the right of that is an interior wall. So an interior wall, why do we worry about an interior wall? We have interior wind load. You probably never felt interior wind load, or not that you were aware of anyway. But we get interior wind load. The simple example is you're a room on the perimeter of the building and the window's open. When the wind blows, you get an influx of air, you get an outflux of air, and the pressure in that room changes relative to the adjacent room. And that's interior wind load. So there's not a lot of air movement. It's a pressure difference between one space and another space. It can also happen due to mechanical system kicking on. You get a fan evacuating air in one room and not another room, can generate interior pressure. The rule that we use for most interior pressures is 0.24 kPa, which is 5 pounds a square foot, which is very small load when you're looking at a small area, but accumulate that over a big area and it's actually significant. So we design most interior partitions for 0.24 kPa. If we are in a loading dock, say, where there is a big opening that can't be relied on to be closed in the event of a storm, we might design that for as high as 0.48 kPa or 10 pounds a square foot. The rule for an interior wall is similar to an exterior wall, where the approach is similar, but now our thickness is H/36. So that same 3.6 meter tall wall can now be 100 millimeters thick, as long as it's a partition, and not a load-bearing wall and not an exterior wall. And once again, if you look at the top, we can see the little clip angles. So we don't want partitions becoming an unintended load path either. So again, there we are. So I talked about the load being transferred back to the structure with the brick ties. You can see in the upper right, this is a very simple suite of brick ties. Each one's have various advantages, but they're all very similar. So you can see what happens here is the backup block gets built, the brick tie gets laid in the mortar joint as you go, and you wind up with a block wall with a whole bunch of brick ties sticking out of it. Then the membrane, the insulation are applied, and then the brick is built up. And the brick, now you have to make sure that you match your mortar joints. Your mortar joint for your block has to match your mortar joint for the brick. Not that inconvenient, because the height of a block is 3 brick courses, is very standard. So almost always that's the case, unless you're into an oversized brick. So making sure the mortar joints align is actually not problematic at all. Lower right, you can see how the approach in a wood building. Now you can see there's lots of layers not represented here. This is really just intended to show the brick tie. So the membrane and insulation aren't shown. But brick tie in wood construction, you can see it might just be a bent piece of metal, and the metal has a whole bunch of corrugations. And the corrugations are there to grab the mortar and make sure it doesn't pull out. On the left, we see dovetail anchor slots. So the black and white diagram shows a concrete wall with a dovetail anchor slot cast into it. So that would typically be a piece of bent steel gets cast into the concrete wall. And now with this slot, you can take this dovetail anchor. This is the dovetail. You slip it into that slot, rotate it 90 degrees, set it into your brick, so that it provides the ability to transfer load out of the plane of the wall back into the backup also slides vertically. When we're dealing with concrete block or steel stud, we don't have mortar joints that happen to line up with our brick mortar joints. We need our dovetail anchors to be able to slide vertically. And the diagram on the bottom left is sort of self-explanatory. This is a dovetail anchor slot screwed through the insulation into the stud backup, and the brick tie slips in that. I'm going to go back. Sorry, I hate jumping around on you. I just forgot to point this out. So this rule is the H/20 rule is for concrete block. For cast in place concrete, it's very similar. We're just using H/25. Cast in place concrete, we don't design by rule of thumb. We design by calculation. Cast in place concrete is always load bearing or almost always load bearing. So we've got to do the calculations, but it winds up being about H/25. So 25% more slender than block. Okay. Here's the other way to use concrete in your envelope. Here is an amazing house by Angela Tsemensis, who's a Toronto architect. This is a concrete house. In this house, concrete was used for everything. So concrete is the structure, it's the water shedding surface, it's the water resistive barrier, and within the concrete wall is the thermal insulation. It's also the vapor barrier and the air barrier. So how does that all work? This is a mass system, or a storage system, or a mass storage system, which is the term that I incorrectly use. It is not a rain screen. See, the layer that we do not have is a drained cavity in this wall. So water hits the surface of the wall. A lot of it is deflected, runs down the face because it's a water shedding surface. Some portion of that water is absorbed into the concrete, and it's just absorbed and stored there until the relative humidity outside drops down to the point where the water can dry, and then it simply dries. It is a vapor barrier. I think the rule is that 2.5 inches of concrete is thick enough to be an effective vapor barrier. So we're not worried about vapor migration through this. There's enough thickness. Also, where's the vapor going to go? The insulation, your dew point is going to lie in that insulation there. It is a closed cell expanded polyurethane. The dew point can be there. It doesn't matter. The vapor can't migrate into the polyurethane. When we're dealing with built-up assemblies, a nice rule is that the effective thickness is 2/3 of the sum of the thicknesses. So let's say that this is a 250 millimeter wall with 50 millimeters of insulation suspended in it. So now we have 100 millimeters of concrete, 50 millimeters of insulation, 100 millimeters of concrete. And those two, there's no shear transfer between the concrete. It's non-composite. Say the thickness of that wall is. It's not 250 millimeters because we have no interconnection between the two wides of concrete. So it's not 250 millimeters. It's not 200 millimeters because a 200 millimeter wall is very thick. But it's not 100 millimeters because there's two wides. So we use 2/3 of the sum. 2/3 of 200 millimeters, 133 millimeters. That's the effective thickness of that wall. And so when we're evaluating using our H/25 rule, 133 millimeters is good for just over 3 meters of height. 25 times its thickness, or 25 times the effective thickness. This is an example of massive masonry. And we don't build a lot of massive masonry in current construction, but so many of our heritage building stock is massive masonry. These are really important buildings. We need to preserve them. We need to understand how they behave. So a massive masonry wall is really nothing but masonry from the outside face to the inside face. And it typically is load bearing and it's thick. So the rule of thumb is something I don't remember. I mean, I've seen this published somewhere, but the rule of thumb is something like 2 withes of brick will carry 2 stories, after which you add a withe for every 2 stories, I think, something like that. Anyway, so you start with 2 withes of brick, which is about 190 millimeters as your basic unit, and you get thicker the taller you get. And then you might add pilasters for your concentrated loads. So that would be for a brick wall. The one on the left is a limestone wall from a heritage building in Kingston, I believe. Now, here's the thing about masonry. I'm going to grab some books to give you a little example. Similarly scaled books off my shelf. So we consider masonry to have 0 tensile strength. Of course, it has some. If you have 2 bricks and you bond them together with mortar, you can't pull them apart by hand. There's a tensile bond there. But you take those bricks, you put them through multiple freeze-thaw cycles. There's not a bad chance that a crack is going to propagate. And 10 years down the road, you're going to pick up those 2 bricks and they're just going to pull apart. So we consider masonry to have 0 tensile strength. If you remember from structures, when something is bending, when a beam is bending, you have tension on the bottom and compression on the top. It's pulling on the bottom, compressing on the top. That's beam behavior. So if you have bending, you have tension. Walls are subject to wind from the outside. They span as a beam from floor to floor to floor. And so they have bending on them. So you've got a wall that's got bending on them. You're building some bending results in tension, and you're using a material with no tension capacity, and somehow it works. The way that it works is that if you have no tension capacity, but you apply compression, you can overcome the tension that would have been there. So these beams are spanning, these books are spanning between my hands. They are not failing in tension, notwithstanding the fact that they are not glued together, right? So if we apply sufficient compression, we can overcome the tension that it would have had, and it gives it bending capacity. A mass masonry wall has the weight of the building on it. It's got its own weight, and it's got the weight of the building above. So it's in compression. So what we do with a mass masonry wall is we ensure that in all load cases, sorry, my table's wobbling around. That's got to be disconcerting. We make sure in all load cases that there is no tension on the wall, that there is sufficient compression, that there's no tension on the wall. This is a storage system like the thermomass. So you can see that a massive masonry wall, there is no rain screen, there's no drain cavity, and yet these walls have historically performed reasonably well. A thing that we need to be sensitive about, though, is that they rely on heat loss for drying. So the heat from the building migrates out of the building, carrying the moisture with it. And that's what keeps the wall, preserves the wall. It keeps it dry over time. So it's not a great wall thermally, which is why we don't build them this way anymore, and they're more expensive, but it's not a great wall thermally. And yet you're going to be involved in projects where you need to improve the thermal performance in a mass wall is we presume that little of the water migrates through the wall. We just take that for granted. The water is not migrating through the wall. We put a small amount of insulation on the inside to improve the thermal performance, and we put a vapor barrier on the inside so that water vapor migrating out can't condense within the wall. But we make sure that we don't over insulate that wall, because we don't want the wall to get too cold. We do want to continue to lose a little bit of heat through that wall. We want just enough heat to continue the vapor migration to the outside so that the wall dries. We don't want the exterior wall at outdoor air temperature, where the moisture that it gets from the rain is going to freeze and cause spalling of the brick and things. So, spalling of the brick. So what does that mean? You probably haven't encountered that. So brick gets saturated, the water freezes, and you know that ice takes up less or more volume than water. Water is one of the few solids that expands when it freezes, which is why ice floats. So it expands as it freezes. It's expanding now inside the brick wall. If it expands too much, it'll actually break the brick apart. And so the surface of the face of the brick will fall off. And this is what's called spalling. This is a rammed earth wall. Rammed earth wall, from a performance point of view, is very, very similar to mass masonry wall. So it's a water shedding surface. It's a water resistive barrier built into one. It does not have a drained cavity. It is a storage system. It absorbs the water and then it dries. It is a thermal insulation, but a poor one, but a non-zero thermal insulation. It is a good thermal mass. So if you are in a desert climate, it is a terrific wall. Heat up during the day when it's hot, and radiate that heat back to the inside at night when it's cold. So it's a terrific wall system in that respect, but it absorbs a lot of water. So rammed earth is almost concrete. It's so many ways it's concrete. It is very fine aggregate. It is a small amount of water. It's a small amount of cement, Portland cement, mixed in there. It is some coarse aggregate. It's all the constituent elements of concrete. The difference is that the cement content is very, very low, which is what makes it more sustainable than concrete. Or at least has lower global warming potential than concrete. Cement content is very, very low. Water content is very low. So you put just enough water, just enough cement to bind it together. But because of that, it's slightly porous. It actually absorbs more water than concrete, which means we have to dry more than concrete, which means that it is suitable in places where there's relatively low rainfall. So this particular building is built in a desert climate. It's an artisanal construction. It's very difficult to reinforce, because you can imagine that well, the diagram on the back shows how it's built. So you set up two forms, you pour in a layer of the earth mixture, you ram it and compact it, often with hydraulic rams, and then you do the next layer. The earth is not just what you excavated out of the site. You might use the earth you excavated out of the site, but it would be quite convenient. It would be quite lucky if it happened to meet all the criteria. What we need is well graded earth, which means we need a certain amount that passes through a fine sieve, a certain amount that passes through a medium sieve, a certain amount that passes through a coarse sieve. And by properly grading it, all the particles can align very densely. If it's not well graded, let's say it's only the coarse material. You've seen gravel, right? Gravel is very open. There's a lot in gravel. That's not what we're after in rammed earth. We want all the airspace full of stuff. And the way we get that is by well graded, by making sure that it's well graded. So we have well graded material. We put it in layers, we compact it, and but you can imagine that if we have that wall full of rebar, it becomes very difficult to compact. So they're largely unreinforced walls, and it's very labor intensive, which is what makes it an expensive artisanal construction. A lot of labor, fairly limited in its utility because of our inability to put proper reinforcing in it. Let's look at light steel framing. So you remember the commercial wall that we talked about. This is the one that has a brick veneer, drained cavity, insulation, membrane, or water resistive barrier, and then studs, a sheathing, and then studs in the backup. And we don't put insulation in the stud cavity because there's no point. It's not doing anything for us. We lose so much heat through the studs that insulating the cavity has very limited utility. All the insulation goes on the outside. Steel studs can be used in a load-bearing or non-load-bearing application. So this particular diagram, these steel studs are load-bearing. And so they would be a slightly heavier gauge. If you walk on any construction site, you are going to see lots of non-load-bearing steel studs. They're very fine gauge. They're quite flimsy looking. But once they're built into a wall, they're much heavier and much more robust. So how do we deal with light steel studs? Similar to block from your perspective as the architect, because you're owning what the non-load bearing assemblies are, we use a height to thickness ratio. The thickness has to be at least the height divided by 30. So you can see that it's thinner than a concrete block wall. Your overall wall assembly is thinner if you use steel stud as your backup wall. The load gets transferred in using brick ties in a manner fairly similar to the quite similar to the block wall, and that the steel stud partition or steel stud wall carries the wind load. H over 30 is our thickness. H over 50 is the thickness for our interior partition. So partitions can be very, very thin. Look at this detail up at the top. This is called a slip track. So with a stud wall, we have a track, top and bottom, the studs in between. The studs are screwed to the tracks. That's your standard construction. In a non-load bearing application, we have a slip track, and a track, and they're not connected. We have one track connected to the structure, one track connected to the stud wall, and one slides inside the other. This too is about allowing the slab above to move up and down relative to the slab below, and prevents our stud wall from becoming an unintended load path. So easy to understand the standard wall assembly, but we do at windows. If we come over to the left of the big diagram, the condition on the right, condition number 3, is the standard condition. We have a track on the bottom for our stud wall. We have studs. We have a track at our sill. The track at the sill has to act like a horizontal beam and span the width of the window and take the wind load to my jambs or my primer studs. So that's a very simple way of doing it, and that's appropriate for small-ish punched openings. If our window gets bigger and bigger and bigger, at a certain point, the window size is such that a track can't span the width of the window. It's just not strong enough and stiff enough. And so we have to do something else. In that case, we might put a box beam at our window sill. And the window head detail would be similar to the sill detail. I only drew the window sill detail, but they're quite similar. So we do a box beam. We take two studs like this, two tracks like that, and we make ourselves a box. And we screw that to the top of our knee wall. And that becomes the element that spans horizontally over the width of the window. Where we are longer even than that, we do hit a point where we can't do it out of a box beam. We build red steel into our wall assembly. It's called red steel because typically it shows up primed on the to the job site, and primed with red oxide primer is a common way. So light steel frame building often has red steel in it, and the red steel is put into the project where needed, where the demand exceeds the capacity of the light steel framing. Down at the bottom here, you can see a plan detail, and similar to the sill detail, for a small opening, we just might have a simple stud. Where the opening is bigger, we might put a bond beam in. Where the opening gets bigger, we might put a bond beam in, we might put a built-up section. And if it's bigger still, we might put some red steel in. How do we determine the size of our studs? Well, this is a decent rule of thumb, and if you follow this rule of thumb, you may not have optimal, but generally you'll stay out of trouble. But that's not how we size studs. We size studs coming to a table that looks a little bit like this. So the first column shows all the stud designations. And you can see that the row headers or the column headers at the top show forces. Those are wind loads from 0.2 kPa up to 1.5 kPa. And then within each wind load, there's a common header. There's a column header that describes the performance expectation. So L over 240, L over 600, 360, L over 600. Those are the allowable deflection under the wind load. So where I've got the column that's highlighted, you can see I've calculated my wind load 1 kPa. And then I looked at the finishes in my building. And I said, this building does not have sensitive finishes sensitive to deflection. Maybe it's a light industrial use or something. And so I can use the most generous deflection criteria, L over 240. And so now I've got this column, and I move down the column until I see a number that is equal to or greater than the height that I need. So and so you can see that I hit 4.5 meters. That I've determined, that's my floor to floor height. And then I scroll to the left, and that tells me what my designation is. You can see that my major rows, each one of those is a stud designation. There are 3 rows associated with each stud designation. They're the various spacings of the studs. So I knew that I wanted a 400 millimeter center to center. 400 millimeters of very convenient spacing. Our bat insulation is 400 millimeters. Our rigid insulation for the outside is 400. We know our drywall spans 400 nicely. So 400 millimeters on center is very convenient spacing. So I chose the 400 millimeter one. So this is how we would go about sizing our studs. zoom in here a little bit. And then here, in the bottom left, shows you how to read this. So the first number in our designation, now every manufacturer is going to have their own designation, by the way. So this is Bailey. Somebody else is going to have a slightly different designation, but they're all going to carry the same information. There is a number that says the depth. So with Bailey, 600 being 6 inches. There is a letter designation that tells you if it's a stud or a track. There is the flange width. So remember that the stud is sort of C-shaped. First number is the depth. Second number is the width. So 1.62 is 1.62 inches, or 1 5/8 inches wide. And then the last number is the material thickness. So studs are made with various thicknesses of material, and that particular example, 54 1/1000ths of an inch. So these are imperial designations. Look at corrugated steel, where that fits in. So corrugated steel is not the backup structure. Now, corrugated steel is in lieu of brick veneer on the outside, but it's an element that has structural demand on it, and it's worth talking about it. So corrugated steel is on the outside as our water shedding surface. The typical span to thickness ratio is about 60 to 1. So the demands on this are very low. It's only carrying wind load. Generally, it doesn't even have a significant deflection criteria. It's allowed to deflect, and it deflects horizontally, or it spans horizontally, like on the image on the right, or vertically, like the image in the middle. Either one are acceptable. So we take, maybe it's 20 millimeters thick. It's 20 millimeters thick. It'll span 1.2 meters. Now I've checked that against published literature. It seems improbable. That's a long way to me, but that's what the published literature says. So you can see what these wall assemblies look like. There's the one on the right is our commercial wall assembly, where we have studs, we have sheathing, which isn't represented, we have insulation on the outside, we have hat channels. So a hat channel is hat shaped, which is why we call it a hat channel. And it gets screwed to the outside of the insulation through to the backup stud to give you something to screw the corrugated metal to, and to create the drained cavity in behind it. The image on the left doesn't have steel studs in it. The image on the left has liner panels, so that it's a very, very wide, probably 1.2 meter wide, bent piece of bent steel, and the insulation is in between the liner panels. Well, you can see every 1.2 meters, we have steel penetrating through that insulated layer. And so that's a major cold bridge. Liner panels, system with liner panels are low performance, low cost, and they're used in industrial applications. Let's look at some insulated metal panels. This is what they used to call refrigeration panels, because they used them on refrigeration buildings, big industrial warehouses that needed to be temperature controlled. But they're high performance. So an insulated metal panel has steel, insulation, steel. This is a perfect barrier drained cavity system. We have talked about this. You see that it's thermally broken. Where those joints interlock, the steel doesn't form a continuous path from inside to outside. So it's thermally broken, but the joints interlock. The joints interlock in a way that drains the cavity. So air can get past the first joint on the outside there's a vertical cavity, runs down, water runs down and out without penetrating through the second tongue and groove. So it's quite high performance, perfect barrier drained cavity. Rule of thumb for insulation panels, insulated metal panels, is L/40. So 4-meter tall wall, 100 millimeters thick without any trouble. So nice long spans. Let's look at the light wood framing. So this is the residential wall that you can see here. We've got studs as our backup, sheathing, insulation. I mean, working from inside this time, silly. Drained cavity, and then some sort of cladding material on the outside is our residential wall construction. The structure is the studs, of course. So what are the size of the studs? Historically, in light wood frame, the exterior walls were 2x6s, and that was just the default. The reason exterior walls were 2x6s is because a 6-inch insulation batt is, I believe, ARC1043, which met the requirements for an insulated perimeter exterior wall. 6 inches ARC1043. That doesn't sound right. Forgive me, I don't remember exactly what they, maybe ARC14 for a 6-inch wall. Anyway, it doesn't matter. Whatever it was, it's a 6-inch wall because the insulation requirement could be achieved with a 6-inch batt historically. But when this became the default, we weren't looking at cold bridging, so we weren't looking at the holistic performance of the wall. We were looking just at the performance of the insulation within the cavity without acknowledging all the other flanking thermal heat loss paths. And now we can't do that. We have to prevent thermal bridging. We can't simply insulate our cavity. That's not an acceptable wall anymore. Once we're putting insulation on the outside anyway, then the stud backup can be determined by the structural demand, not the thickness of insulation. And a 2x4 exterior wall is just fine for small buildings. 89 millimeter 2x4 exterior wall. The depth to span ratio for a stud wall, generally the thickness has to be greater than L/24. So what does that tell you? 2.4 meters tall, 100 millimeters thick. Now that's nominal. So when I say nominal depth is L/24, nominally 100 millimeters, 2x4 meets that. So 2x4, the actual dimension is 89, the nominal dimension is 100. So we're good. We can use a 2x4 as our backup wall. We can use wood studs up to 6 stories. Here's the thing. We rely on the exterior wall to resist lateral loads in our building. So the diaphragm keeps it square in plan. The perimeter walls keep it square in elevation. Those are shear walls. That wall needs the sheathing on the outside to be able to resist lateral loads. If we take the sheathing on the off, it'll simply collapse. So we rely on the sheathing on the outside to resist lateral loads. There are a bunch of products on the market now that are insulated sheathings. I think they might call it zip sheathing or something. There are products on the mall that are insulated sheathing that don't have wood directly in contact with the stud. This can be beneficial because it prevents a thermal break, a cold bridge. It allows you to build it without the layer of insulation on the outside of the sheathing. So it's beneficial in that respect, but it's structurally a bit problematic. So for small buildings, fine. Like if your building is sufficiently small, it's fine. because you've got drywall on the inside, and that's going to carry a certain amount of the burden. It'll carry some lateral loads. It is a panel product, but the capacity is much less. High capacity, we need OSB or plywood on the outside. So this is something that is currently evolving. Envelope demands and standards are going up, and the better envelope solutions are driving down the structural performance. And we've got to find the sweet spot in the middle where the envelope performance, because we need great envelope performance, no question. We need zero operating carbon in our buildings. That is a non-negotiable. We're not there yet, but we'll be there by 2050 for sure. So zero operating carbon in our buildings. We need great envelopes, but we also need to meet our minimum threshold for structural performance. This is a structural insulated panel. These are proprietary products. It's looks like an Oreo cookie. It's got the white icing in the middle and the biscuit on either side. The biscuit is a sheet of OSB, which is oriented strand board, chipboard, and the icing in the middle is EPS, expanded polystyrene insulation. EPS is not the best. It's an open cell. You can get condensation within EPS, but it's economical. And if I haven't said it before, I'll say it now, that what we need is just that much more than minimum. So striving to have extremely high performance is unnecessary. So for the structure, we need our floors to carry 40 pounds a square foot. So we'll design to 45 pounds a square foot. We might be at 41, 42. We are getting no value back designing our structure for 100 pounds a square foot if that is not the demand on the structure. So we get no value back. EPS is not the best insulation, but it's good enough. You better to spend more money making it a bit thicker and having more insulation than using a higher quality insulation product if the lower quality product is going to do the job well enough. So EPS core, OSB on the surface. It's a composite system, so they're glued together, which means that the EPS core can transfer shear from one to the other. And so it acts, even though the EPS or the OSB is only 12 millimeters thick, it acts as a big, thick panel. And so it can span a long way. It's nice and stiff, can span a long way. And you can see that it is thermally broken. There are no cold bridges in this. Now, having said that, they do tend to put a spline in between the panels. You can see that the OSB overhangs by about 3/4 of an inch so that you can put a 2x6 or whatever thickness in there. And then the next one comes along and it just gives you something to nail your OSB to, top and bottom, so that the two panels are joined together. So it's like a nailing strip. This is a familiar looking table, sort of like the steel stud tables, but just very slightly different. They flipped this table. You can see that where the stud table had the performance levels in columns, this has it in rows, but it doesn't take long to figure out how to read this. So what we do, I don't think I highlighted the columns and rows in this one, so I'll just have to talk you through it. What we do is we figure out what our span is and what our load is. We go to the panel span column, and then we slide down until we find a load that exceeds our loads. So this is the table that describes the allowable load based on various spans. So you know your span, and you scroll down the column until you hit your load or hit a load that exceeds your load, and then you move left, and that tells you what your overall thickness of your SIP needs to be. And you can see that for each SIP, we have, again, 3 performance criteria based on deflection limit. Oliver 360 for finishes that are vulnerable to damage. Oliver 240 for ones for finishes, but less vulnerable to damage, like a suspended acoustic ceiling, for example. And we would use Oliver 180 if there is no finish. Straw bale walls. So straw bale walls, this is another artisanal product. This is a very low carbon, low global warming potential product, but it is an artisanal product. It relies on a great deal of manual labor to construct. This is in the image is my brother and sister-in-law. They've built a number of straw bale homes for themselves. Um, um, a straw bale wall has high R value. It's 18 inches thick, so 450 millimeters thick. High R value up to R40. But look at the range. R18 to R40. R18 is a pretty good wall, but it's not great. I mean, it's comparable to a 2x6 wall with bad insulation in it. So it's not great, and that's all to do with different moisture content and different packing density of the straw. The straw is structure in the sense that it is wind bearing. It has to span. It's effective as a structure just because it's so thick. It's similar to the mass wall in the sense that it doesn't have any tensile strength, but it's heavy enough and thick enough that we would have no tensile stresses. The straw bale wall consists of the straw bales and a plaster skin inside and outside. The plaster skin is the water shedding surface. It is not a great system from a water management point of view. It's a mass wall. It is not, there's no drain cavity. And because of that, we need to manage wetting. We can't afford to have this wall getting saturated. So you can see in this image, they've built deep overhangs to protect the wall. It's a storage wall, so the water that does get into it has to be able to dry to the outside. So your skin needs to be very vapor permeable to keep so that you can ensure that it dries. CLT. CLT is cross-laminated timber. It's primarily used for structure. I mean, the only function within your assembly tends to be structure. But in fact, it does more than that. So wood is a reasonable insulator. It's not the best, but it's reasonable. And so your thick layer of CLT also has an insulating function. The diagram you see is the clip system by Element 5. So this is a pre-manufactured wall system that consists of CLT, a membrane, insulation, a series of clips that hold on a track or a channel to which the exterior cladding or water shedding surface can be attached. I didn't indicate a rule of thumb for CLT. So let's use L over 36 for CLT. I wish I could write it on directly on here, but unfortunately I can't. But L over 36 is a decent rule of thumb for CLT in a non-load bearing application. So it can be fairly thin. CLT, it is all glued together. And so that glue is a fairly effective vapor barrier. So we don't really have to worry about condensation. It'll prevent vapor migration. This example, this in image here, is the McEwen School of Architecture by Levitt Goodman. We were involved as the mass timber specialists on that project. It was a Stantec project, I think, from an engineering point of view. Okay, let's talk very briefly about glass. So glass is a perfect barrier system. So while it's absolutely impermeable, but it is discontinuous. So it's perfect barrier with drain joints. The perimeter of glazing has to deal with the water. The glass itself needs to span to the frame, and then the frame spans to floor. There are several types of glass. This glass could be a whole lecture on its own. So forgive me, I'm going to skip over it. Glass fiber has an extremely high strength, like 1,000 MPa, 3 times as much as steel. Very, very strong stuff. The trouble with glass is that if any little imperfection and a crack can begin to propagate, to the point where it will fail completely, at a stress much lower than the strength of the material. So high strength material, but also high probability of flaws, and the flaw will precipitate a failure, not overload. The way we manage that is we keep the stresses low. So conventional annealed glass, we consider to have tensile stress of about 20 MPa. We can heat strengthen glass, which brings us up to 40 or 50 MPa, or tempered glass brings us up to 80 or 100 MPa. The reason there's two numbers is that within the field of the glass, away from the edges, the probability of a strength reducing flaw is less, and so we use a higher allowable stress. So for annealed glass, we use 25 MPa in the field of the glass, and we use 20 MPa around the boundaries of the glass, where the probability of the strength reducing flaw is higher. Okay, so what is it about the heat strengthening tempering process that gives us higher strength? It does not change the material. So the material is identical in all cases. What differs? So if we take glass and we heat it up, it all expands, and it's in a semi-molten state. Now we rapidly cool the glass. It compresses, it shrinks. It shrinks more rapidly on the outside than on the inside. So you've got a condition as it's cooling where the outside is shrinking more than the inside. And then it cools, and the inside catches up. So the outside is shrunk more, the inside catches up. Now, as the inside is catching up, it is compressing the outside, and the outside is stretching the inside. So we wind up with a stress profile through the glass where we have compression on the outside and tension on the inside. Okay, so how does that help us? Well, the reason it helps us is that a flaw in glass is much less detrimental if the glass is in compression. So you don't get compression doesn't propagate cracks. It's in compression. And the place where you're likely to get the flaw is on the outside of the glass, not in the middle. So having a little bit of compression on the outside and tension on the inside just reduces the impact of a strength reducing flaw. And so we have higher usable strength. Back a slide here. We can also talk about laminated glass. So where we have where we have high demand on our glass, we can laminate multiple glass lights. A light is a sheet of glass. Multiple layers of light laminated together. The interlayer in between them is perfectly clear. So you experience laminated glass all the time in your life. The windshield of your car is laminated glass. So you get multiple layers of glass laminated together to improve strength. You also experience tempered glass all the time. Now, you've all had the experience of walking down the street on a Saturday morning, Sunday morning, and you walk past a bus shelter, and there is a pile of tiny little shards of glass. That's tempered glass. Tempered glass, when it breaks, a crack propagates all through the glass very rapidly, and the glass completely shatters and voids the opening. That's because if a flaw gets through that compression layer into the tension layer, there's very high tension in that layer, and so it just forces the crack to propagate everywhere. So that's tempered glass. You experience tempered glass all the time because the side windows of your car are tempered glass. You smash the car side window, it will completely void the opening. But it's very high strength. The windshield of your car is laminated and not tempered. You might say, well, why wouldn't we use tempered glass? It's stronger. The problem with using tempered glass on your front windshield is that it will completely void the opening. And so that's problematic, obviously, if you're driving and suddenly you have no windshield. But also, even if it's laminated so that it doesn't void the opening, the cracks propagate everywhere and you can't see, and that's also problematic. So we use laminated glass for the windshield so that it has the strength benefit of multiple layers, so that breakage doesn't pass through the laminated layer, so that it doesn't void the opening and you can continue to see, and it's safe enough to stop driving. So we use different types of glass in different situations in order to manage the hazard of breakage. This is the most important slide that I am going to share with you today, probably, because as architects, the finger is going to be pointed at you if there's glass breakage, because glass is an architecture assembly. The reason it's important for me to teach you this is because the finger's going to get pointed at you when there's glass breakage, and you are going to turn around pointed at me, say, well, glass broke. What am I to do about that? I'm just the architect. It must be a structural problem. So let's look at glass breakage because it's very helpful. So breakage under load, top left. This is what glass looks like if it breaks under load. So like too much snow load on a skylight, you'd get breakage that look like this. Too much wind load on a window, you get breakage that looks like that. And that is if it's supported all the way around on all four sides. So cracks that more or less start from the middle and migrate to the perimeter radially, and then annular cracks that join the radial cracks. Two edges supported. So if we have glass and frames on two sides, but free top and bottom, the crack migrates radially to the supports. So you can see the cracks are only going to the supports on the two sides. And it's not compound curvature. Generally, two edges supported. It's what do we call it? It's monoclastic. It's not a compound curve, and so we don't have the annular cracks. Four edges supported. It's synclastic curvature, compound curvature, curved in both directions. That's what generates the annular cracks. Two edges supported. It's monoclastic, and so we don't have annular cracks. Breakage due to a soft body impact looks a little bit like the like breakage under uniform load. So you see cracks radiating from the impact site to the boundaries, and a nice pattern of annular cracks connecting those. Hard body impact, we don't tend to see the annular cracks. It's just cracks radiating from the impact site to the perimeter. The Hertzian cone, you've seen this. So what happens when here's my glass, stone hits this side? That's compression, right? You get compression on that side. Compression doesn't break things. Tension breaks things. But that tension, that compression here will dislodge a cone of glass on the far side. So you've seen this on your windshield of your car from time to time. I don't know if you've ever noticed that you've got this stone chip. You can see it, you can't feel it. You touch it on the inside, there's nothing there. It's because it's laminated glass. The stone chip is in the outer glass light. It does not progress through the inner glass light. That's why we laminate glass. Okay, the most important diagram is thermal stress. So thermal stress failure is characterized by a crack that starts at the perimeter and wanders lazily around through the pane of glass. Thermal stress failures occur when you've got part of your glass is hot and part of it cold. If this glass is hot, it's trying to expand. If that glass is cold, it's trying to contract. The glass that's cold is now being pulled apart by the glass that's hot. And so you wind up with your glass in tension as a result. Somewhere on the perimeter, you're going to get a tiny little flaw, and there's going to be sufficient tension that a crack is going to start to propagate from that. So you have experienced these. Probably you've been in a car that has a thermal failure in the windshield, and you'll see that this lazy crack just migrating around. They generally start just above the dash, and they start just above the dash. Does that make sense? They start just above the dash because when you've got your heat on, you're blowing a lot of hot air up on the windshield, but the bottom might be in contact with something cold. Okay, the reason it's so important for you architecturally is, I'll give you a few examples. I had a project. There was an atrium. There was a big overhang and a big south-facing window in this atrium. Very cold day in the winter, sort of 30 below, but bright sunshine. So the top of the window was shaded by the overhang, and below that it's exposed to the bright sun. And so the bottom warms up, the top stays cold, and we wind up with a crack migrating down from just under the roof, migrating into the field. Another example, again, a south-facing window, winter time. In this case, there had been snow and then a cold, sunny day, and the bottom portion of the window, there wasn't snow in contact, but the snow shaded the window. So there's enough heat lost through the window, even an insulated layer, that it melted the snow a little bit. The snow wasn't actually in contact with the window, but it did provide shade, and we wind up with a thermal crack starting at the bottom and working its way up. My most embarrassing thermal crack story is I owned a pub in Scarborough at one time, and while I was renovating the pub, I didn't want people to see in and see that there might have been tools to steal. So I taped black garbage bags all over the walls, or all over the inside of the window. South-facing window, cold day, but bright sunshine, black surface. The sun hits, absorbs the black surface, warms up the window on the inside, cold from the outside, and I broke my front windows. So the important thing is that we recognize the thermal thermal stress or thermal failure, as soon as you recognize it, it's obvious what caused it. And I remember asking a window supplier, "What do you do about that? Do you just design everything with higher strength glass?" Because thermal stress is somewhat unpredictable. We can't evaluate how much thermal stress there is going to be in order to prevent it. And his answer was, "It's unpredictable. You don't want to burden your whole building with heat strengthened glass because of the possibility of a thermal failure. What you do is you use regular glass everywhere just to conform to the building code. If you get a thermal failure, when you replace the glass, use heat strengthened, because now you've identified a condition that's vulnerable to a thermal failure." Okay. We're going to take a very quick break here because my coffee's empty and it's very early in the morning, and I will be back in just a couple of minutes. Okay, let's look at window systems. So the first one is punched windows. So a punched window is a window in a frame. The frame, the glass spans to the frame spans to the frame spans to the framing. Punched windows in wood frame are generally combustible. They're wood or vinyl. Punched windows are generally pre-glazed. And often operable. In a commercial building, they are generally non-combustible, fiberglass or aluminum. They may or may not be pre-glazed. They may be glazed in the field, and they are often non-operable. So punch windows span to the framing. The framing might be wood, it might be steel stud, it might be concrete block, it might be concrete. Okay, here's the one you're going to deal with most frequently. This is curtain wall. Curtain wall consists of three components. There's the glazed panel. Remember that any glazing system, perfect barrier drain joint. Curtain wall consists of the glazed panel. It consists of the structural frame, which is an aluminum extrusion, and a cap and pressure plate on the outside. So the extrusion is a slightly complicated shape that is intended to provide a structural box. We call this the back box. This is a rectangular aluminum extrusion, and it has complicated features on the outside that receive gaskets that a gasket can slip into, and also can take a screw. And the reason we need it to take a screw is because the channel is in the field, the curtain wall extrusion is installed, the glazing is applied, and then a cap comes on, or a pressure plate comes on and gets screwed to retain the glass. And then it's capped, visually capped. Because the pressure plate is screwed to the back box and the cap is a tight fit, it's a friction fit, but it's a tight fit, they tend to structurally, they act as one unit. So there's enough shear transfer due to the screw and enough friction in the pressure plate that they act composite to each other. The back box can be reinforced with steel channels inside. Channels simply slipped into the back box to give it an extra strength. If you see the little diagrams in the upper right, we can take the complicated part, the part that receives the gaskets and the screw, and just extrude that without the back box. And then we can take that part and screw it to something else. So we can imagine that we can screw it to structural steel. This allows us to take advantage of the extra strength and stiffness of structural steel as our mullion, as opposed to aluminum. Steel is 3 times stiffer than aluminum. So the members can be smaller if they're steel. So our project in Assiniboine Park, we used a steel curtain wall system. You can also screw them to wood. So now we can, in our mass timber building, we can apply a veneer extrusion directly to the mass timber rather than having a separate curtain wall system. According to Wikipedia, curtain wall is an exterior covering of a building in which the outer walls are non-structural, instead serving to protect the interior of the building from elements, may or may not be glass. So non-structural cladding is considered to be curtain wall, particularly if it runs past the edge of the structure. So and I'll show you what I mean by that in just a sec. So curtain wall doesn't have to be glass, but colloquially speaking, when we talk about curtain wall, we're talking about glazed curtain wall. Okay, how do we size curtain wall? Well, the method is not all that different, except that here it's represented graphically instead of in a tabular form. So we can see that we have a graph for a specific a separate graph for each mullion assembly. So the one on the left is 6 inch, the one on the right is a 7.5 inch, and we have a curve for loading that relates the mullion height and the mullion spacing. So The wider the farther apart the mullions are, the more load they pick up, and the taller they are, the longer the span is. So both of these have an impact on structural performance. So what we would do is we would determine our load. In this case, it's 20 pounds per square foot, which is fairly common for a low-rise building. 20 pounds a square foot for wind load. So that tells us that it's curve A. If you look at the little table in the upper right, it tells us we're looking at curve A. We know our mullion center, our mullion spacing is 5 feet. We've determined that architecturally that we have mullions every 5 feet. So we trace up the 5 foot column until we hit our curve A, which is 20 pounds a square foot. Then we migrate to the left, and you can see that our maximum span is 11 foot 8 inches or 11 foot 6 for a 6-inch channel. So let's look at a rule of thumb for that. 11 foot 6 divided by 6 inches, 23. So rule of thumb that we might infer is L over 23 for a curtain wall system in a low-rise building. Let's move over to the right here. And again, we have 5 feet on center, 20 pounds a square foot. We're going to go up our 5 foot column to our curve A. Over to the left, we have 14.5 foot maximum span for a 7.5 inch deep channel. 14.5 feet divided by 7.5 inches is 23. So same rule. So it's a nice reliable rule that works for the 6 inches and the 7.5 inch section. Now, obviously, this is just a rule of thumb. I've based it on 5 feet because that's a fairly common. That is a fairly common glass size. If your glass size is smaller and your mullions are more close together, then it can be your L over 23 might be L over 28. If they're wider, then it might be L over 18. If your loads are high, like if you're at the top of a high rise where your loads are high, your L over 23 is going to fall apart. So like any rule of thumb, it's contextual, it's reasonably reliable within a range of application. So let's look at window wall then. I've got a diagram. I'll show you what window wall is. But where curtain wall is fairly easily understood, you build a structure, you put your frame on the outside of the structure, you apply glazing from the outside, and you have a nice continuous wrap around the building. Window wall is glazed from the inside. So your cladding system goes from slab to slab. It's more economical because of that, because it's simple, it's to glaze from the inside, but it's discontinuous. Your window wall is discontinuous at your floor, and so the performance is less. This gives you a sense of a summary for window wall and unitized curtain wall. So with window wall, your maximum width is 6 feet. Curtain wall, it's 8 feet. Window wall, your maximum height is 11 feet. Curtain wall, 15 feet. Window wall maximum area is 45 square feet, and curtain wall is 75 square feet. So what we're seeing is that window wall is suitable for spans and heights roughly 25% less than curtain wall, which is the reason, or one reason, why we tend to see window wall in residential applications. And when I say residential, I'm talking about condos, and curtain wall in commercial applications, because commercial applications, we have taller floor to floor height, and we want bigger glazing units. I'm going to ask you to bear with me for 1 second. I just got the your battery is running low message. So I better go get myself a battery. Sorry about that. Went and grabbed a battery, and the battery wasn't charged. So I went and grabbed another battery. It wasn't charged either. And then I couldn't find an extension cord. And in the meantime, my computer shut down on me. But thankfully, I was still connected with my cell phone, so the meeting didn't end. So apologize for the big pause in the middle. So we had been talking about curtain wall. This is window wall. So remember, L over 23 was our rule of thumb for a curtain wall. Window wall, and that's about 25% farther than window wall, which would suggest that window wall can span about 75% of that, maybe L over 18, something in that range. So the detailing, you can see the diagram on the left. This is a fairly typical curtain wall detail. We have a couple of clip angles into the edge of a slab that carries the aluminum extrusion, which goes past the edge of the slab. Excellent from a thermal point of view. So the clip angles can be thermally broken, and the pressure plate is thermally broken from the back box. So high performance from a thermal point of view. But you can see that we've got this condition here past the edge of the slab where we have the potential for acoustic transfer. We've got thermal transfer past the slab. So we've got smoke potential. So that's not an ideal condition. But now look at the glazing. You see the upper glazing above the mullion in the curtain wall system? Is it clearly an IGU, an insulated glazed unit with an airspace? That's an insulated condition. Below that, you see only a single glazing, which might imply that we have single glazing there and it's a cold problem. But what that's called is a spandrel panel. So this is a panel of glass. It's not an insulated glass. Often it's back painted. So it's opaque. And what is not indicated here is that there is an insulated assembly between the spandrel panel and the edge of the slab. So this isn't telling the whole story. This isn't glazing slipping past the slab, clear glazing slipping past the slab so you can see all this junky hardware. This is a spandrel panel. It's opaque. It's an insulated assembly between the glazing and the slab. Okay, so that's the curtain wall on the left. On the right is window wall. So window wall, you can see some familiar elements. You can see an aluminum extrusion, an extrusion that's got all this complicated bits to pick up gaskets to receive the window. It's got a cap on top of it to retain the glazing. So similar elements to what we see in the curtain wall, but you can see that the glazing sits on top of the slab and comes up to the underside of the slab with a caulk joint, and the slab goes through to the edge. Dotted in here is a window wall spandrel panel. So a separate piece that's installed from the outside to cap and insulate the edge of the slab. So it's not a radiator condition like that image I showed before, where the slab edges are exposed to view and simply radiating heat to the outside. The slab edges are covered with a nominally insulated cover. This is load-bearing glass. So in this particular case, the Apple store in New York, we have glass fins to make it load-bearing. Lots of interesting things in load-bearing glass. So load-bearing glass can be insulated. Load-bearing glass is always laminated glass, because if it's load-bearing and there is damage to a glass light, you can't have your structure collapsing. So use a laminated glass, and it might be quite thick. Like you can end up with 40 millimeters thick glass. You know, it could be 4 10-millimeter glass lights with a clear interlayer in between. The challenge of glass, interestingly, in a load-bearing application, I always presumed that buckling is what controls. But it seems that in load-bearing glass, once you satisfy your deflection criteria for wind, which I didn't share actually when we were talking about glass, you can have up to something like 1% deflection of glass under wind load. So it's quite a bit. You see the other rules we were talking about: Elever 180, Elever 240, Elever 360 are normal deflection limits. For glass, it's more liberal than that because there's no finish attached to glass. It is the finish, and glass can tolerate a lot of movement. So load-bearing glass, we might have 4 laminations of 10-millimeter glass, but then it can be made into an insulated glazing unit as well. So you might have 4 10s, an airspace, and 2 6s, or something like that. So you wind up with quite thick assemblies in load-bearing glass. And then the joints are silicone. The most challenging thing about load-bearing glass is how do you get the load into the glass? Is it maybe this is worth saying actually. So the thing you don't see in a window are the setting blocks for the glass. You have a great big window frame all the way around. You might be inclined to think that the glass is continuously supported on the bottom. In fact, the glass sits on 2 points in the 2 corners, 2 little hard rubber blocks in the corners. And in plane, the glass spans to the corners of the frame. The frame is not carrying the weight of the glass, or it is, but only just in the corners. But the frame is carrying the wind load. So where we've got the glazing sitting on top of the load-bearing glass walls, it probably is the same. We've got a couple of setting blocks in the corners. The glazing sits on that. There is a silicone joint, but the silicone joint is there to hold it together and keep water out. It's not intended to be the primary load-bearing element. This is an image of the Integral House. This is a wonderful project designed by Bridget Shim and Howard Sutcliffe. We've got all kinds of glazing in this one. So the image to the left, you can see we've got wood curtain wall. So the frame was installed and it was glazed after from the outside. The image in the middle, there's an art wall, a glazed art wall inside the house, suspended on cables with little bronze castings that were designed by Howard. And then the image on the right, this is the most interesting thing to talk about today. This is a glass scrim. The upper part is a glass scrim. Glass fins bolted to the back of the house, and then glass adhered to the glass fin using very high bond tape, VHB tape, very high bond. This is the same tape that is used to hold the windshield on your car. This is an image showing cable glass. So cable glass is from an envelope performance is the same as curtain wall, but rather than having an aluminum back box, we have a cable. Look at the image in the upper right-hand corner. So that very fine cable is in lieu of the aluminum back box. And then the glazing is only picked up at the corner points. It's not picked up continuously around the edge. As a result, the glazing has a slightly higher structural demand. You remember that the curtain wall rule of thumb was the depth needed to be the height divided by 23 was our approximate rule of thumb. That's the structural depth. If we take a cable and we pull it tight, as long as it's straight, it cannot resist load. It resists load by deforming. It has to have shape. L over 23 is about how much depth you need to resist wind load. We're designing cable systems for a deflection of L over 50 to L over 36. So here we have a 10-meter tall wall at the tallest point, or maybe even 12 meters tall. I think it was 12 meters tall at the high point. The anticipated movement of that cable was 240 millimeters. So we need as much space as though it were curtain wall, or close to as much space as though it were curtain wall. It's just that the space isn't, there's nothing in that space. It's just deflection room for the cable when the wind blows, for the cable to move out of plane. But you can see the impact is you don't have a big mullion in front of it. When you take a cable and span it 40 millimeter, or sorry, 12 meters, and you pre-stress it in order to limit the lateral deflection to L over 50, you have very large forces. And this is one of the major constraints of cable glass. Imagine that you have an atrium and you want to do cable glass. So you connect the bottom of the cable to the foundation, connect the top of the cable to the floor above, and you pre-stress it. That works pretty well until you have a party on the floor above, and that space gets full of people. Now you're adding load to the floor. It starts to sag a little bit. Your cable goes slack. So you lose your pre-stress because the beam starts to sag a little bit. So you either have to make your beams extremely stiff, so that even when loaded above, the cable doesn't go slack, or you have a separate beam. You have a beam that carries the floor, and you have a beam that carries the cable, and the beam that carries the cable only carries the cable. It's probably the smarter solution. On this project, the cables were tensioned between the top and bottom cord of a truss. So at a relatively close spacing, the two boundaries were pushed apart by the web of the truss, and the deflection in the truss wasn't, or the size of the elements top and bottom were not controlled by how much they sag in between the webs. They were controlled by the deflection of the truss overall. So they were, from the point of view of the cable glass, they were extremely stiff, and so that it was a good system in this case. Okay, I just explained this to you. I forgot I had this slide in here. So this is just a little explanation of catenary systems. A catenary system doesn't work without sag. Sag is a short form of the word sagitta, which comes from Sagittarius. Sagittarius was the mythical creature that had a bow and arrow. So when you think of Sagittarius, think of bow and arrow. That gives you a sense of the shape and where the name came from. The sag is the distance between the curved cable and the fictional straight line between the two boundary points. Sag implies loose. When we think of something being saggy, it's something that's loose. But in fact, sag can be extremely, you can have an extremely rigid system with sag. So the edge cable in a tension element, in a tension fabric structure, for example, curves. It curves, therefore it has sag, because the sag is just the distance between the curve and between boundary points. So even though it's very rigid, a catenary system cannot withstand load. I said this a minute ago, cannot withstand load without sag. So even if you start straight, the forces are infinite. Once you start to apply load and it starts to acquire a little bit of sag, now the forces start to drop off. And so the sag will keep increasing until the forces, until you find a balance where the force, where the resistance to load is equal to the force in the catenary. One thing that I wanted to point out here is, and this is something that I want you to get in your head because it is so often misunderstood. I'll tell you in the context of shade sails. We do a lot of tension fabric structures. Shade sail industry lives slightly outside of the code world. And a lot of people bringing shade sails in, believing that the forces are fairly small because the sail weighs next to nothing. So if you have a sail that weighs next to nothing, you're tend to inclined to think that the supports can be very light. That's wrong thinking. So the let's look at this little diagram on the right, or the little set of calculations on the right here. The tension in this catenary, WL squared over 8 times the sag, is how we calculate the tension. You do not need to remember that. The sag is L over 50. That's what we said our deflection limit is for our cable wall. And that's a fairly normal limit for a tension system, L over 50. Substitute that back into the first formula, we get tension is W50 WL over 8. And the reaction perpendicular to the force is WL over 2. So what I'm saying, look at the very left end of the diagram. What I'm calculating is the tension and the perpendicular reaction. So the perpendicular reaction is how much force does it take to just carry the weight of your shade sail, is the perpendicular load. And compare that to the tension in the shade sail under load. All of this, I apologize, that was a long way to get us to this. The tension in this case with a sag of L over 50 is 12.5 times the perpendicular load. So your shade sail might carry 15 pounds a square foot of wind load. That might be your design condition. 15 pounds a square foot of load perpendicular. And so based on the area, you might end up with 500 pounds perpendicular load on your shade sail supports. And lots of people stop thinking there. 15 pounds a square foot times 30 square feet, 450 pounds. That's my vertical load. It's nice and light. Anything can take that. The lesson here is that if the perpendicular load is 500 pounds, the in-plane load is 6,000 pounds. The in-plane load is dramatically higher than the perpendicular load. But the perpendicular load is the one that we can get our heads around. So people dramatically underestimate the amount of in-plane load. That is the whole purpose of this slide. Do not underestimate it. So where does this affect us? Well, it affects us if it's a shade sail, obviously. But think about hanging a banner off the side of the building. The banner is fairly small. And they don't pick up a lot of load, but those brackets at the top and bottom of the banner, sure, they're picking up load in this direction, but that banner is pulling those brackets together by a force of 10 or 12.5 times higher than this perpendicular force. And you'll see this all over the place. Like, start watching for catenary systems and think about that I mean, L over 50 for lots of them is overly conservative, but like if you think 10 times, whatever load is applied normal to the surface, the in plane or normal to the surface, the in plane load is 10 times that force. Okay, let's look at some tension fabric structures. There's a range of them. We can do a whole lecture. I mean, I've done lots of lectures actually on tension fabric structures. It's a big topic. But generally, we break them into a few major categories. One, frame structures. A frame structure is the one where there is a frame and it's got fabric on the cover, and the fabric has to span from frame to frame, but the demand on the fabric is relatively low in a frame structure. The other is, and we just call them tension fabric structures, I guess, where there isn't a frame. There might be a mast, there might be a boundary element, but there isn't a frame per se. And a tension fabric structure, the shape of the fabric is what it allows it to span. In a tension fabric structure, the fabric is the structure. It might be the primary structure, like on the right, the Denver airport. It might just be the secondary structure, the spanning between primary structure. But fabric serves a structural function. It carries load. It is your water shedding surface. And it is a water resistive barrier. So a fabric structure is a perfect barrier system. It's a perfect barrier system with minimal. The image on the top left is the St. Louis Park Arena, fabric covered glulam arches. That whole roof is one piece of fabric. So it's a perfect barrier system that is virtually jointless, or often virtually jointless. It is your thermal insulation. Now, having said that, the R value is damn close to zero, but it's not quite zero. And also remember that the air film has an insulative value. So the fact that the fabric is there means that a very small film of air is static on either side, and that gives you some insulation. So the R value of the fabric, next to nothing. But to the extent that there is a thermal barrier, that's what it is. Fabric can be used in insulated buildings in a couple of ways. We can have two layers of fabric with a very thin layer of insulation in between and create an insulated fabric. It's not common, but it's done. We do that sometimes for like hockey rinks or something, a fabric covered hockey rink. Or like the image in the bottom left, you can have an outer fabric, which is structural, and an inner liner fabric on the inside of your structure, and then a dead air space in between. So the dead air space in between has an insulative value, and you can even put batt insulation in between the two layers. So not ideal envelopes, but not terrible either. Remember, if you just have an air, the conductivity of air is extremely low, but if air is allowed to convect, it effectively increases the conductivity because you're continually moving hot air away and replacing it with cold air. So your delta T across your boundary is high, which is why we put the batt insulation in. It stops the movement of air. This is a diagram of an air-supported or air-inflated structure. Well, this is a diagram of an air-supported structure. So we could use pneumatic structures in two different ways. This one is a structure where we occupy the pressurized environment. You have to walk through an airlock to get in and out of one of these. Like any other fabric structure, perfect barrier. The structure is structure. It's water shedding surface. It's the water resistive barrier. It is the thermal insulation to the extent that there is, and it's the air and vapor barrier. The inflation pressure of a dome like this is typically 0.24 kPa, 5 pounds per square foot. Increase that to 10 pounds a square foot in the winter. The reason we increase it in the winter is that in the winter we have the potential for snow load, and we can only carry as much snow as the inflation pressure. We can't carry more than that. So you can see we've got an inflation pressure of 480 pascal, or 0.48 kPa. Does anyone remember what the snow load in Toronto is, roughly? All right, I'm going to give you a hint. It's roughly 1 kPa, so twice the inflation pressure, which means that the 1 in 50 snow load will collapse an air-supported structure. Air-supported structures rely on secondary means to make them safe. Often, historically, they have melted the snow off. They just pump a bunch of heat in, and you lose enough heat to melt the snow off. I don't believe that is permitted anymore. And so they rely on manual clearing. Like they put a rope over it, and they have a broom tied to the rope midway. And you get somebody on one side pulling and then pulling back and forth, and they saw over the dome to remove snow. The proportions are extremely important. We're using a height of roughly a third of the span for an air-supported structure. And you can imagine that, if we have 0.48 kPa of inflation pressure, that's got to go somewhere. That goes into the boundary foundations. So the uplift on this thing is huge. The foundations need to be able to take it. So the foundation demand for an air-supported structure is very high. ETFE is a foil. It's a fabric foil. So most fabrics consist of a structural scrim. It's a weave of very high strength polymers. And then it'll have a coating on it to keep it waterproof. ETFE is a foil. That means that there's no fibers, there's no orientation. It's just a solid material all the way through. It's very strong fabric, very weak compared to other fabrics. Fabrics rely on curvature to withstand load. That was my sag diagram, and you could see that the higher the sag, the more load it can carry. Or the higher the sag, the lower the fabric stress under a given load. For ETFE, we need a fairly tight curvature in order to be able to sustain significant load. So we end up with a maximum span of ETFE of about 3 meters with a sag of L over 10. So a sag of about 300 millimeters on a span of 3 meters for ETFE. The Assiniboine Park Conservatory, you can see all the pillows are spiral pillows. They run from the core to the perimeter of the building. The reason they're spiral pillows is not just a formal decision. I mean, it does create a very interesting form, of course, but it's not a formal decision. What we needed is a continuous pillow to go all the way from the core to the perimeter of the building and not be more than 3 meters wide. First idea, orient the pillows radially. Sounds good, right? You start 3 meters wide at the perimeter of the building, because that's the maximum span. You're about 200 millimeters wide when you get to the core. They converge. You wind up with big triangular pillows. Not that there is anything particularly wrong with a triangular pillow structurally, but you can imagine that a long skinny triangle has twice as much boundary for the same surface area. The problem with that is that the cost of the system is in the boundary. It's not in the foil. The foil's cheap. The extrusions are expensive. So cost of the boundary is expensive. And our objective on this project was to minimize shading. So having twice as, and it's the boundary that shades. So having twice as much boundary increased the shading quite a bit. So 3 meters, 3 meters for a linear pillow. If we have a two-way system, so Eden project is a two-way system. It's all hexagons connected together. Those can be bigger, up to 6 meters. So two-way pillows, 6 meters, one-way pillows, 3 meters. Single layer, we can go up to about 1.5 meters for wind load, or 750 millimeters. I didn't indicate this, if it's going to carry snow load. So single layer ETFE is flat. It doesn't have that much curvature. It needs to start to sag in order to carry load. You start, because it's single layer, you pull it flat. You have a flat system. It begins to be loaded, it sags, and that's what gives it the carrying capacity. With ETFE systems, we have multiple layers. That creates a pillow, and the dead airspace gives it some R value, so that we actually get decent energy performance out of an ETFE. Like our air-supported structure, ETFE systems are inflated to 0.24 kPa in the 0.24 kPa in the summer, 0.48 kPa in the winter, which means that under snow load, the pillows collapse. The snow will squeeze all the air out of the pillow. Sounds problematic. It's not great for insulation, obviously, but there's a really wonderful passive system here, that you have a high R value normally. If you get snow, squeezes all the air out, collapses, now you have no R value. The heat from inside begins to melt the snow on the boundary layer, and it becomes extremely slippery. Now you've got the snow becomes slippery, it slides down the pillow and slides off the building. As soon as the snow slides off, you haven't turned the fans off. It squeezed the air out, but the fans are still running. As the snow slides off, the pillow reinflates. The other nice thing about that is you've got multiple layers of ETFE. When they collapse, now the snow load is being shared amongst several layers of ETFE. So it's not just a single layer doing the work, it's multiple layers. So here's an image of an ETFE extrusion on the left. What you can see is that the ETFE is clamped under a pressure plate with a gasket. It's a gasketed system. It's drained joint. It's perfect barrier in between the joints, and it's a drained joint. And that's a really important thing to remember, that the joint is imperfectly waterproof. The water will get in there. This particular example, you can see that the extrusion sits in a steel trough. The idea there is that the water gets into the extrusion, drains through the extrusion onto this little steel channel, and is directed out of the building. But it has to be a drained joint. The image on the right is our from Assiniboine. These are our partitions. So these are single layer ETFE partitions. Those vertical cables are every 1.5 meters. We put the partition above, so the bottom 3 meters is vision glass. I mean, vision glass just meaning glass, but it's glass because it's because it's because it's super clear. You can see through it, obviously. So glass is clear. We wanted there to be a view through into the botanical garden from the public space. Above 3 meters, ETFE is slightly cloudy in appearance. So it lets lots of light through. It actually lets more light through than glass, but it diffuses the light slightly and changes the visual impact. So we used glass up to 3 meters and then ETFE up above it. This is a system called Facet. This is a water shedding fabric. This can be used on all kinds of buildings. This particular example is a parking garage where it's used in a single layer. It's structure and water shedding surface, but nothing else. And in fact, I mentioned that most structural fabrics are a woven scrim of a high strength polymer, polyester generally, with a coating that makes it waterproof. The fabrics that are used in a system like this are generally uncoated fabrics, so they're air permeable, but they do cut down the wind a great deal, but they are air permeable, and you don't seal the edges or anything. It really is the water shedding surface, but you can see from the details just how minimal the details are. You're not seeing any of the shenanigans. That's all hidden behind the fabric. My goodness, I made it. Okay, so that's our lecture on the structure of enclosures. I am going to give you there is going to be a quiz on this one. Hopefully it's an easy quiz. Here. And we do not have, yeah, we've got Lisa Miller Way coming in to talk about fire next week. Hopefully, fingers crossed, we get our classroom back. And I'll see you next week. If not, we'll find a way to give you the fire lecture virtual like this one. Okay. See you very soon, I hope, team. Take care.